Okay, let's look at this box on an incline problem. So let's just first go through the setup. We have this orange wedge of mass m1, and it's on the ground, and the ground is frictionless, so this wedge can slide left and right without friction. And then stacked on top of the orange wedge is this blue box. And this blue box has a mass of m2, and the surface between the wedge and the box is also frictionless. So this is frictionless, and this is frictionless. We also have gravity acting on the system right here. And we have our two bases set up. We have this one right here. This one's fixed to ground. And EX just points off to the right, EY points up, and EZ is out of the page. And this is our inertial frame. And then we also have this other basis set up. It's green. And this is actually also an inertially fixed frame. It points down the ramp. It's pointing down the ramp at some angle, theta. And since theta is not changing, this green basis is always going to be pointing. It's always going to be oriented in this direction. These unit vectors on this green basis never change. So it's inertial. It's an inertial frame as well. It's just setting a direction. Okay, and what do we want to do for this problem? We want to find the equations of motion to define the system. We want to find the reaction force between M1 and M2. And we also want to find the force between M1 and the ground. So there's some force here between M1 and M2. We want to define that. There's another force here between M1 and the ground. We're going to find that. And we're also going to find the equations of motion that will tell us how M1 and M2 are going to move. So how many of equations of motion do we expect to have? Well, the number of equations of motion are equal to the number of degrees of freedom of your system. In other words, how many parameters do we need to completely define the position of every object in the system, right? For this problem, it's going to be 2. We're going to need to define 2 things, right? We need to define where M1 is on the ground, right? Where M1 is on the ground, and then where M2 is on the wedge, right? M1 can slide left and right, and M2 can slide up and down. So we need to define those 2 states. And down here, I have this little note. Assume M2 will never touch the ground. It's always going to be sliding on M1, right? So our box is never going to contact the ground down here. Just assume it's always going to be sliding on M1. Okay, so let's start by defining our direction cosine matrix that relates the red basis to the green basis. So as we say before, the red basis has EX just pointing off to the right, and EY is pointing straight up, and EZ is out of the page. All right, so that's the red basis defined. And then we said that EX, this green EX, is pointing down the ramp. And if we just do some simple geometry and we extend this ramp up, we'll see that this angle here, it makes an angle of theta with the horizontal. And if we use the concept of vertical angles, we know that this angle here is also theta. And so if we draw these red and green bases on top of each other, they look like this, where the angle of theta is here. And I have a lot of videos talking about setting up your direction cosine matrices, so I'm not going to go into too much detail about this, but what you'll see here is that to go from our red basis to our green basis, we have to rotate the red basis by an angle of theta about the negative EZ direction. Or you could state this as you have to rotate by an angle of negative theta about the EZ direction. Okay? And that's all I'll say on that. I have plenty of videos talking about setting up direction cosine matrices. So this is our application of the fundamental 3 rotation matrix. And, we're going from this red basis to this green basis. And to do that, we had to rotate the red basis by an angle of negative theta about the EZ direction. So that's why we're using our fundamental 3 rotation matrix. And we know that cosine of a negative angle is just cosine of the angle, and sine of a negative angle is negative sine of that angle. Okay, so this is our relationship between the red and the green basis. Note, the angle of the incline does not change. It does not change. So theta is a constant. This is a little different from what we've done in other problems where theta was changing. Theta is just a constant here this time. The derivative of theta is 0. The slope of this wedge does not change. And Ex, Ey, Ez, the green basis, that does not rotate. So the derivative of these Ex, Ey, Ez, these are going to be 0. Okay, so Dex, same for Dey and Dez, this is going to be equal to 0. Okay, because they're not rotating. It's not rotating. It's an inertial frame. Okay, green and red, those are both inertial frames. Okay, so kinematics. For the kinematics, our goal is to find the absolute accelerations of m1 and m2, and we're actually also going to do the center of mass of the system. And so first, we must find the absolute positions so that we can take the derivatives. So let's just start with m1. We're going to pick some arbitrary inertially fixed point to measure from, and we're going to measure to some arbitrary point on the body m1. So my notation I chose to use was, I'm going to use like this red X, or not red, I'm going to use this purple X for point O, which is going to be inertially fixed. It's going to be fixed to ground. And then I'm going to use this orange circle, this orange dot, and I'm going to call that point P, and it's going to be fixed. That's the point that's fixed to M1. So I drew like a T0, I guess, drawing over here where O and P are right on top of each other. And then after some time, the wedge is going to move some distance. I don't know, it's going to move right, left, we don't care. It doesn't matter. And so over here, this shows after some time, the wedge has moved, and it's moved a distance of x1. So to get from O to P, we have to travel x1 in the EX direction. It does not matter what you pick for O and P, as long as O is fixed to ground and P is fixed to the wedge. The reason it doesn't matter is because those are just constants. Those are just constants, and when you take the derivative of those to get the velocity and the acceleration, they get sent to 0. Let me go through this down here real quick first, and then I'll show you what happens if you pick just like a general point. So like we already said, the position vector to get from O to P is, it's just x1 in the EX direction. So that's exactly what we have written here. We take the derivative of this, and we're just going to be left with x1 dot in the EX direction. Remember, we're applying the product rule here, right? We're really doing, and I'll just write this in pink. We're really doing the derivative of the first, which is x1 dot, times the second, EX, plus the first, x1, times the derivative of the second, which is dEx dt. But this term, this goes to 0 because the derivative of a inertially fixed unit vector is 0. It's not rotating. So that's that. That's what we're doing. And yeah, we get the velocity, and then we do the same thing to get the acceleration. We take the derivative, we're left with x1 double dot in the EX direction. So why does the point not matter? The point doesn't matter that you pick, and it's arbitrary because say we pick some random coordinate for r, and it was it's equal to x in the EX plus, I don't know, say we went down a little bit, like down here, and we call that plus y in the EY direction. Well, y is a constant, so when you take the derivative of this, you're just going to be left with x dot EX plus y is a constant, it's 0, right? That's why the point you pick doesn't matter. As long as you're consistent in the points that you use, as long as you're measuring from an inertial frame, inertially fixed point, it doesn't matter. Those constants just go to 0, and your velocity and your acceleration are always going to be the same. They're always going to be correct regardless of the points you pick. Okay, and that's exactly what I said down here. Note, it doesn't matter what inertially fixed point we pick. It also doesn't matter which point we pick that's fixed to m1. It's arbitrary and doesn't affect the final value of the absolute acceleration, which we just saw, because the constants, they just go away. They just go to 0. So let's do the same thing for m2. Again, we're going to keep our purple X as our inertially fixed point, O. We're going to keep our orange dot as our point P that's fixed to M1. And now I'm going to introduce this blue triangle, point Q, that's fixed to M2. Again, just arbitrarily pick. I pick different locations for O, P, and Q this time, but O is still inertially fixed. M is still, point P is still fixed to body 1, M1, and Q is fixed to M2, right? It doesn't matter where you pick them. And so, this was our T0 picture, and after some time, the wedge is going to move some distance horizontally, and then M2 is going to move some distance up or down the wedge. I still define the distance from O to P as x1. That hasn't changed. But now I've defined this distance x2 from P to Q. And so our position vector that defines point Q, which is body 2, is the sum of the vectors that take us from O to P plus the vector that takes us from P to Q. And so what that looks like is right here. So to get to body 2, measured from an inertially fixed point, we traveled x1 in the EX direction. That gets us to point P. And then we traveled x2 in the green EX direction. And that got us from our inertially fixed point to point Q. And when we take the derivative of this is just me expanding out the product rule. So the derivative of the first times the second plus the first times the derivative of the second, right? Our inertial unit vector here, rate of change goes to 0. So we're just left with x1.ex. And then again, another application of the product rule right here. And we're left with x2 dot in the green ex. And so do the same thing. We're going to take the derivative to get acceleration. And this gets us x1 double dot ex, red ex, plus x2 double dot green ex. And that is our absolute acceleration of the box. Okay, finally, let's find the absolute acceleration of the center of mass of the system. So from the previous video, we know that the acceleration of the center of mass is equal to the sum of the acceleration of all the bodies multiplied by their respective masses divided by the total mass of the system. And so for our system, we have 2 bodies, so it's m1 times a1 plus m2 times a2 all over m1 plus m2. This is just plugging in for a1 and a2, and we end up with this right here. This is just plugging in. So our kinematics are done. We have the absolute acceleration of body 1, the absolute acceleration of body 2, and the absolute acceleration of the center of mass. And we're also going to want these useful little calculations down here. These are just some dot products. It's going to become clear why we want to have these. It's going to make it easier later on. I'm just going to go through one, and then you can look at the rest on your own. So we want this red EX dotted with our green EX. So red EX dotted with, this is the green EX right here. And if we look over here at our rotation matrix, green EX is equal to cosine theta red EX minus sine theta red EY, 0 in the EZ. So this right here, this is the green EX. And when we dot product this, we get just cosine theta because EX dotted with EY is 0. So we just end up with cosine theta. And then we do the same thing for these other 3. All right, moving on. So now we're going to look at the kinetics. So this is where we start looking at the forces that are acting on our system. So there's 3 free body diagrams that we can draw. The first one is of just the wedge, just M1. The second free body diagram we can draw is just the box, just M2. And the third free body diagram is M1 and M2 together, the whole system as one. So let's just quickly go through these free body diagrams. So what are all the forces acting on the wedge? Well, we have gravity pulling the wedge down. We have the normal force of the ground acting on the wedge. That's what keeps the wedge from just falling through the ground. It's this normal force. And then we have this reaction force of the box, M2, acting on the wedge. So now we go over to the second free body diagram of just the box. Again, we have the force of gravity acting on M2. And then we also have this reaction force acting on M2. It's the exact same as what's acting on M1. except it's in the opposite direction, and that follows Newton's third law. For every action, there's an equal and opposite reaction, right? So if the reaction force is acting this way on M1, it must be acting in the opposite direction on M2. And then finally, over here, we have our third system, which is M1 and M2, the whole system together. And so here we have the force of gravity acting on M1, that's this one. The force of gravity acting on M2, that's this one. And we have the normal force. Notice that we no longer have R because R is an internal force, right? When we look at the system as a whole, that's an internal force, and it's not something that's acting on the system externally. So this is our free body diagram. So which one do we use, though? There's three of them. What do we do? Let's just go through all of them and see what information we can get from each. So looking at free body diagram 1, the way I personally like to set these up is I draw my free body diagram, I draw my my coordinate bases, and I put my forces off to the right here. So that's what I'm going to do. Force of gravity acting on M1. Force of gravity is equal to mass times g, acceleration due to gravity. And which direction is this force acting in? This direction is in the negative EY direction. So this is mg in the negative EY direction. Okay, so our force of gravity is minus m1g EY. The normal force of the ground acting on the wedge, well, the way I drew it, it's acting in the positive EY direction. It doesn't matter the direction you define this n, because in reality, like, we don't really know. It could be acting this way. Intuitively, we know it's not, but if you drew it this way, it's okay. Just make sure you would have a negative sign here. The signs take care of themselves as you go through this process. It doesn't matter. You can just guess the direction as long as you are consistent. And then R, the way we drew R, is in the negative green EY direction. So it's R in the negative green EY direction. And so those are all of our forces. And we're just going to apply Newton's second law. F equals ma. So this here is just rewriting directly, copying all of the forces. That's F equals, this is m1 times a1, the acceleration of body 1. We just found that. That is on this page right here. This is this right here, x1 double dot ex. Now let's go back down. x1 double dot ex. So this is Newton's second law. And the only other thing I did was collect the EY terms right here. All right, so that's our equation from the first free body diagram. Let's go to the second free body diagram. This is the box. So again, I draw my free body diagram, I draw my bases, and then I'm going to put my forces off to the right here. So R on this one is pointing in the positive EY direction. Remember, Newton's third law, equal and opposite. This force needs to be opposite of this force, okay? So, yeah, R-EY, R is acting in the positive EY direction. And then same thing with gravity on this one. It is, the force of gravity is mg, and it's acting in the minus EY direction. So here's our forces. Again, we're just going to write Newton's second law, F equals ma. A2, let's just remind ourselves what A2 was. A2 is right here. And that's exactly what we have written down here. It's just plugging in. And we're distributing M2. So this is M2, A2, and this is just our forces. All right, let's keep going. This is free body diagram 3. Same thing with gravity. I'm not going to go through it again because we already did it. And then N is acting in the positive EY direction. So here's N. Those are all the forces acting in our system. And we're going to do F equals M times the absolute acceleration of the center of mass. This was copied right from above, but this is the absolute acceleration of the center of mass that we found. These are our forces. This is M1 plus M2. M1 plus M2 cancels in the denominator here, so we just end up with this equation right here. So now that we've looked at all of our free body diagrams, let's go look at what information we can get from each of those equations that we came up with. So let's kind of remind ourselves what we're looking for. We want to find n. We want to find this n. We want to find an expression for this r. And then we also want to define the motion of body m1 and m2. And so what we need is an expression for x1 double dot and x2 double dot. Those are differential equations of motion. So these are 3 free body diagrams that we analyzed, and their respective equations that we got from each of them down here. So looking at these equations, I immediately see some things that kind of catch my eye. I see in this equation 2 that r is all by itself right here. If I can somehow get rid of this term, I'm left with an equation in terms of some constants, x1 double dot and x2 double dot. And then I also see in this equation 3 here, if I can somehow get rid of this whole term here, again, I'm just left with an equation in terms of some constants, an x1 double dot and x2 double dot. Well, that'll be 2 equations, 2 unknowns. I can solve for x1 double dot and x2 double dot. So let's do that. What do I have written here? There's different ways you can manipulate these equations to find n, r, x1 double dot, x2 double dot, right? I'm just going through one possibility. This is how we're going to go about finding those equations down here. So if I take equation 2 and I dot this with the green EX, well, green EX dotted with green EY is 0. This term is going to go away. If I look at equation 3 and I dot this with red EX, well, red EX dotted with red EY is 0. This will go away, right? And I'm left with these 2 equations, 2 unknowns. And then with that known, if I go back to equation 2 and I dot it with green EY, if I go here and I dot it with green EY, I'm left with an equation for r in terms of constants and x1 double dot and x2 double dot, which we already have equations for. Those are already known now. So now I know r also. And then finally, if I go back to equation 1 and I dot this with red EY, then now I have an equation for n in terms of r, some constants, and x1 double dot. R is now known, x1 double dot is now known, now I have an expression for n. So let's go ahead and just plug through some of these numbers. I'm not going to talk extensively through these. I'll just kind of let you look at them, but I'll talk through the first one. So I'm taking equation 2, and I'm dotting it with EX, dot with EX, dot with EX, both sides. EX dotted with EY, you're going to end up with that down here. EX dotted with EY, this is going to be 0. That's getting rid of this R term. And then you have EX dotted with red EX, that's this right here. And then EX, green EX dotted with green EX is right here. That's going to be 1. And this is why we went through that trouble of using those helpful calculations before of doing those. Because now we can just say EY dotted with EX. Well, where was that? That was this one right here. That's just equal to negative sine theta, and just plug in that right in. Red EX dotted with green EX. Well, that's this one right here. That's just equal to cosine theta. So I'm just going to plug in cosine theta. And then this was 1. And so I have my first equation, x1 in terms of x1 double dot, x2 double dot. I'm going to go quicker through this one. This is 3 where we're dotting with a red EX. If we go through this process, we're left with another equation in terms of x1 double dot, x2 double dot. This is this one and this one. This is a system of 2 equations. So 2 equations, 2 unknowns. We know x1 double dot and x2 double dot now. Let's keep going. We're going to dot equation 2 with the green EY. And I encourage you to pause the video and actually work through this. I'm just going through it quickly, but I think it's written out pretty clearly here. And we're going to be left with an equation r for r in terms of x1 double dot. But we already know x1 double dot from this system of 2 equations, 2 unknowns. And then finally, we have, we're going to dot equation 1 with the red EY, and we'll have an expression for n in terms of r and some constants. And r is now known from here, and r was known from here. So those are all of our equations and expressions. I modeled this system in Open Modelica, and so let's hop over there and take a look at the system over there. Okay, so here we are in Open Modelica. I modeled our problem two different ways so that we could check it. This first way that you're seeing here is the actual physical model, right? I have a prismatic joint so that mass 1 can move to the left and right, and then I angled it, with some, angle theta, which I think I set to 45 degrees, and I have M2 on top that can slide on M1, right? So this is just the physical representation and model of our system that we just worked with. The other way that I modeled this in Open Modelica is over here. I actually coded it up. So Modelica is a programming language, and you can see this first section called model. Block on plane equations is what I called it. This is where you define all of your states and variables and everything. We have this initial equation section here, and this is where we set our initial conditions. And then finally, our equation section here, this is what's really nice about Open Modelica, is you can just type the equations as they are, right? And it's not like other programming languages where you have to have just one thing on the left of the equal sign. You can see here, I just wrote out the entire equation. So if you take a second and look at these are exactly what we had written in our notes here. And so this is solving this system of equations. And I solved both of these methods, and I plotted the results. And so this first result that we're looking at is the position of M1 and M2. You can see that this bottom one is mass 1, and so it's sliding to the left. It's going more negative. And the results from the equations are plotted in red, and the results from the physical model are plotted in blue, and they're right on top of each other. They're exactly the same. They give exactly the same results, which is good. And then here we have this green and purple. It's a little hard to see, but these are also plotted right on top of each other for the system of equations and the physical model. So x2 is going off to the right and increasing. And so these two are matching, and that's really good. I have this other plot over here, which is the normal force, and these are also right on top of each other. They are equal to, what is this, 23.5 newtons. And then finally, our reaction force between the two bodies is also right on top of each other. So our equations are right. We compared it against the physical model. Everything looks good to me. I'll be sure to put this code and model into the GitHub so that anybody can play around with it. Hope you learned something, and if you have any questions, just let me know. See you in the next one.